And welcome to the section 10.5 video lecture, the last video lecture for chapter 10 in Math 141 Statistics at Morton College. I am Dr. Scott Spaniel, your instructor for this course, once again here with another video lecture. So in this last section, similar to the last section in chapter 5 and the last section in chapter 9 that we just got done with, this is called putting it together. Which method do I use? So there's basically two types of hypothesis tests we've looked at in this section, in this chapter, and we want to make sure we're picking the correct one and which one to use. So you can go ahead and take out your note sheets for chapter 10 and flip to page 17, and we'll go ahead and get started. So like I said, there's basically two different options going on here. You're either dealing with a proportion or a mean. Okay, with a proportion, if n times p times 1 minus p is greater than or equal to 10, then you can use for less than, greater than, or not equal to, you can use 1 prop z test, and for not equal to, you could use 1 prop z int. Okay, if n times p times 1 minus p is less than 10, then what you want to use is for less than or greater than, you can use the binomial distribution. Okay. Similarly, with the mean, if n is greater than or equal to 30, for less than, greater than, or not equal to, you can do 1 prop. Nope, sorry, not 1 prop. You can do the t-test. And for not equal to, you can do a t interval. Okay. But if n is less than 30, then one of a few things needs to happen. Either your population needs to be normal, or you need a box plot with no outliers, or a box plot with no outliers, and the normal probability plot needs to be linear. If that all is true, one of those two is either the first one or the second two are both true, then you can do a t-test or t-interval depending on the situation. Okay, so that's what we're going to be looking at in this section, is which one of these do you pick, and making sure you check all those things before you go and do it, because there are going to be times when you won't actually be able to do any of these options. So what I want to do today, I think, is just run through these first 2 pages of these to look at 3 examples together, and then I'm going to give you all have you pause the video and try the last 2 pages of problems on your own, and then you can hit play and we'll go through them together. So here we go. So in October 1945, the Gallup organization asked 1,487 randomly sampled Americans, "Do you think we can develop a way to protect ourselves from the atomic bombs in case other countries try to use them against us?" With 788 responding yes. Right, so we've got 788 out of 1487. Did a majority of Americans feel the United States could develop a way to protect itself from nuclear atomic bombs in 1945? Use the alpha equals 0.05 level of significance. So the first thing you should notice here is they gave us a sample size, and then they told us how many people in that sample had a certain characteristic. So that right there tells us we're talking about proportions. Okay. Now, in this case, what we're looking at is a majority of Americans. And we looked at an example like this back in section 10.2, but majority just means more than half. So our null hypothesis is going to be that P equals half, and our alternative hypothesis is a majority, which is greater than 0.5, greater than half. And so now we can check this part, n times p times 1 minus p, to see what methods are available to us. So if in this case, n would be 1487, p is 0.5, and then we do 1 minus 0.5. Okay? And we want to see what value we get for that. So we can use ClassCalc for that if we want. And we get 371.75. Okay. So 371.75 is greater than or equal to 10. So that means we can use one prop z test. Okay. So we go into ClassCalc. We do one prop. So you can use the shorthand to get there, which is OPZT, or you can go down here and find it in the menu, right, under test, one prop z test. Okay, and so we put in our P naught, which is 0.5, our X value, which is 788, and our N value, which was 1487. And then we get the values for less than, greater than, and not equal to. And we pick the one that fits the situation we're in. So in this case, we're doing greater than, right, is our alternative hypothesis. So that's the middle one. So our p-value equals 0.0105. So now the question is that less than alpha? And in this case, it is, right? 0.0105 is less than 0.05. And so that means we can reject the null hypothesis, and we can write a statement concluding that the alternative hypothesis is most likely true. So we can write, there is sufficient evidence to suggest the alternative hypothesis, which in this case is that a majority of Americans in 1945 believed we could find a way to protect ourselves from atomic bombs. Okay, so that's the idea. Okay. So the second one. So the manufacturer of toner cartridges claims that the mean number of printouts is 10,000 for each cartridge. A consumer advocate is concerned that the actual mean number of printouts is lower. He selects a random sample of 14 such cartridges and maintains the following number of printouts. So notice, they kind of set you up for this, but because the sample size is small, in this case it's 14, we're going to need to make sure we can do this. And we should be already be able to tell that we're going to be dealing with a mean here, right? Because we were given a set of data. So we're going to need to know the mean for that. And they use the word mean a lot here, okay? So the first thing we want to do is we can check that the box plot has no outliers. And we want to check that the normal probability plot is approximately linear by checking to make sure that R is greater than the critical value. Okay? So we can start out by getting the critical value, right? And so this is in the note sheets for Chapter 9. So it's on page 9 in Chapter 9. And so in this case, our sample size is 14. So we go down here to 14, and we see that 14 has a critical value of 0.935. So we're going to need our R value to be greater than that in order to be able to do a t-test. So I already have this data written out in your note data sheet. So if you're following along with this, we can copy and paste from there into our notes here. Okay, and then we're going to do a box plot of x of 1, and we want to exclude outliers, and we're going to zoom in on that. And when we do that, we see, oops, that didn't do what I wanted to do, really. Let me zoom back in. Okay, we don't see any outliers. Okay, so we should be okay. Yeah. Right, no outliers. So that's good. And then we can do the normal probability plot for x sub 1. And if we want, we can look at the graph of it, and we can see that it's pretty linear. But what we really care about is this R value. So our R value is 0.989. And so back here in our note sheets, the box plot had no outlier, so that's a check, and our R value was greater than our critical value, so that's a check. So even though this is a small sample size, we can use a t-test to do this hypothesis test. So now we can do the hypothesis test. So the hypothesis test, we first write our hypotheses. So the null hypothesis would be that the mean number is 10,000. And then the alternative hypothesis would be that it's less than that, right? Because our consumer advocate thinks that it's lower. Okay. And then we can go into our ClassCalc with our data set already in there, and we can do t-test. Tell it to use data, because we want to use the data that we got up here in x1. Put in the mean, which is 10,000, and then have it calculate the mean and the standard deviation from the data set. And when you do that, you get these values. So we've got less than, greater than, and not equal to. In this case, we're doing less than, right? Because less than was the symbol in our hypothesis test. So our p-value is 0.1012 when rounded to 4 decimal places. And so now we can compare that to our alpha, which is 0.5. And in this case, that's not less than alpha. So that means we're going to do not reject the null hypothesis. And so there is not sufficient evidence to suggest the alternative hypothesis. So there is not sufficient evidence to suggest that the mean is less than 10,000 printouts. Okay. So that's the idea. So there's one where we're giving a data set. And now let's do one more together. So in 2001, the mean contract interest rate for a conventional 30-year fixed loan for a single-family home was 6.3%. According to the U.S. Federal Housing Board, a real estate agent believes that the interest rates are lower today and obtains a random sample of 41 recent 30-year conventional loans. The mean interest was found to be 6.05% with a standard deviation of 1.75%. Is this enough evidence to conclude that interest rates are lower at the alpha equals 0.05 level of significance? Okay, so our hypotheses are here that, notice these are percentages, but they're not treating them as percentages. They're treating them as mean. They're an average as percentages. So these are not proportions. These are means. So we don't have to write them as decimals. So we can say mu is 6.3. And our real estate agent thinks they're lower today, so mu is less than 6.3. And so now our sample size is 41, which is greater than 30 or equal to 30, so we can do a t-test. Okay. So we can come in here. Let me get rid of all of this out of the way. And we can do a t-test with our mu of 6.3, our x bar of 6.05, and our standard deviation of 1.75 with a sample size of 41. And so in this case, we're doing less than, which is this one on the left. So our p-value is 0.1829. Okay, which is not less than 0.05. So just like the one above, there is not sufficient evidence to suggest the alternative hypothesis, which in this case is suggest interest rates are lower than in 2001. Okay, so that's the idea. So the practice here is just more practice with doing these methods, but with the added piece that you don't know if you're going to use one prop z-test or t-test, because you don't know which section the information is coming from. So what I'd like you to do now is pause the video and try the problems on pages 19 and 20. Okay, and then when you're done with those, hit play. We'll go through them, and that'll be it for Chapter 10. So does playing Mozart for unborn babies result in children with higher IQs? A psychologist obtains a random sample of 20 mothers in the first trimester of their pregnancy. The mothers are asked to play Mozart in the house at least 30 minutes each day until they give birth. After 5 years, the child is administered an IQ test. We know that IQs are normally distributed with a mean of 100 and a standard deviation of 15. If the IQs of the 20 children in the study result in a sample mean of 104.2, is there evidence that the children have higher IQs? Okay. So, our null hypothesis is that they don't have higher IQs, so that their mean would be 100. And the alternative hypothesis is we want to know, do they have higher IQs? So is mu greater than 100? And in this case, even though our sample size is only 20, we know the population is normally distributed, so that means we can do a t-test without having to do any other checks. Okay. So then just like the problem we were doing together here, we can come in, do a t-test with a mu of 100, a sample mean of 104.2, a standard deviation of 15, and a sample size of 20. In this case, we get a p-value of 0.1128. So at our level of significance of 0.05, that's not less than alpha, so we do not reject H naught, and so there is not sufficient evidence to suggest playing Mozart raises IQs. Okay. So next one. According to the Insurance Information Institute, the mean expenditure for auto insurance in the United States was $774 in 2002. An insurance salesperson believes the mean expenditure for auto insurance is different now. He obtains a random sample of 35 auto insurance policies and determines the mean expenditure to be $735, with a standard deviation of 48.31. Is there enough evidence to conclude that the mean expenditure for auto insurance is different from the 2002 amount at the alpha equals 0.01 level of significance? Okay. So in this case, because n is greater than or equal to 30, because it's 35, we can write our hypotheses. One is that the mean mu equals 774, and the other one is that mu does not equal 774. And now here you have two options. You can do the normal t-test, or if you prefer, you can do a confidence interval. Okay? So if we do the t, let's go ahead and just do both of those so we can see what those would look like, because this is a difference test, so you can do both. So a t-test, which isn't giving, is being a little weird. So let me write that in again. Okay, there we go. So a t-test with a mean mu of 774, a x bar of 735, an s of 48.31, and a sample size of 35 for not equal to gives us a p-value of 0.0000, right? 3 if you round it to the fifth decimal place. Okay, and then we could also do a t-interval. We don't do both of these, just do one or the other, but if we wanted to do a t-interval, we could do it. With our mean is 735, our standard deviation is 48.31, our sample size is 35, and our level of confidence is 0.99, right? Because it's 1 minus 0.01, and that gives us an interval of 713 to 757. Okay? So those are two different ways to go about this, and either way, you're going to reject H naught. Because over here, that is less than alpha, so that works, so we reject H naught. And over here, we reject H naught because 774 is not in the interval. And we expect mu to be in the interval. So if our guess for mu wasn't in the interval, our old number, then it probably isn't anymore. So there is sufficient evidence to suggest the mean expenditure for auto insurance is different than 2002. Okay, so that's the idea there. Okay, next one. In 2001, 23% of Americans, university undergraduate students, had at least one tattoo. A health practitioner suspects that the percent has changed since then. She obtains a random sample of 1,026 university undergraduates and finds that 254 have at least one tattoo. Is this sufficient evidence to conclude the proportion is different from 0.23 at the 0.1 level of significance? Okay, so first things first, you can write the hypotheses. So in this case, it's P equals 0.23, or H1, P does not equal 0.23. And we now need to make sure that we can do a 1 prop Z test or a 1 prop Z interval by taking 1026 times 0.23 times 1 minus 0.23. Okay, and in this case we get 181.7, which is definitely greater than or equal to 10. So now we can do 1 prop Z test or 1 prop Z interval just like the one before because we're doing not equal to. So we can use either one when we're doing not equal to. So let's go ahead and like the previous one and do both. So 1 prop Z int. So our X value was 254. Our N value is 1026. And 1 minus our alpha gives us 0.9. So we get an interval of 0.225 to 0.270. Okay. And then if we do a 1 prop Z test, our P naught is 0.23, our X is 254, and our N is 1026. And so we get P value for not equal to of 0.181213. Sorry if I'm rounding to 4 decimal places. Okay. And in either case here, we're going to not reject H naught because on this one on the left, 0.23 is in that interval. So it could easily be the population proportion. And here, 0.1813 is not less than 0.1. So in either case, we do not reject. And so there is not sufficient evidence to suggest the proportion of college students with a tattoo is different. Okay, so there's that one. Just a couple more. So flip over here to page 20 and try these. So a certain vehicle emission inspection station advertises that the wait time for customers is less than 8 minutes. A local resident is skeptical and collects a random sample of 49 wait times for customers at the testing station. He finds that the sample mean is 7.34 with a standard deviation of 3.2. Does the sample evidence support the resident's skepticism? Okay. So in this case, we're dealing with means. So mu equals 8 or mu is less than 8. Okay. And our sample size is big enough so we can do a t-test. So our t-test here. Mu was 8. Our sample mean is 7.34. Our sample standard deviation is 3.2. And we sampled 49 wait times. And we're doing less than, so our p-value is this number on the left, 0.0777. So that's not less than alpha, which is 0.1. So we do not reject H naught. So there is not sufficient evidence to suggest the wait time is less than 8 minutes. Okay, and last but not least is this problem that's similar to one of the ones we did before. So it's a small sample. In this case, we only have 12 samples, so we need to check the box plot and the normal probability plot to make sure R is greater than the critical value. So we can go ahead and go into our Chapter 9 notes and get the critical value. Once again, on the homework, they'll give you this to you. But for 12, our critical value is 0.928. So we need our R value to be bigger than that. So we can go into our data set, and we'll copy and paste this into ClassCalc. Then we can do a box plot. X of 1. And we want to exclude outliers and zoom in on that. No outliers for the box plot. The normal probability plot for X1 is, if we zoom in, is very linear, and it has an R value of 0.989. Okay. So both these things check out. So now we can do our t-test. So we'll set up our hypotheses. So H naught is that mu equals 3.2, and H1, she thinks that the new contractor is not getting them replaced as quickly. So that would be mu is greater than 3.2, and we can run our t-test. So t-test with our data, our mu value is 3.2, and our data is in X sub 1. So we get p-values of for greater than of 0.0361, which is less than our alpha in this case. So we would reject H naught and say there is sufficient evidence to suggest the new contractor is not getting the work done as quickly. Okay. So that's it for Chapter 10. We're all done. That's everything we're going to do. Those are all the techniques you need to know how to do in the calculator and by hand. Don't forget to do your quiz and the homework assignments for these sections. And as always, if you have any questions, feel free to send me an email or a remind message, and I'll get back to you as soon as possible. Other than that, I'll see you next time for the first section of Chapter 11.